Okay, so we had started the chapter on fluid mechanics, okay, and we've done half the lecture. Okay, so this chapter consists of two parts. Okay, so this chapter consists of two parts: fluids at rest and fluids in motion. Last time we'd finished this part, we'd studied the properties of fluids at rest. I'm going to review that quickly, and then today we'll study some of the properties or laws that apply when fluids are in motion. Okay? And essentially what we're doing is we're applying the stuff that you've learned the first few chapters to fluids. Okay? All right, so there are three states of matters that you're familiar with: solids, liquids, and gases. Okay. These two guys are called fluids. Okay. And you saw that the densities that we deal with, the density of a fluid, of a liquid, is 1,000 times greater than that. Okay. So for instance, the density of air is about 1.3 kgs per meter cube. A meter cube is this much. Okay, that computer box is a meter cube. So that much air weighs about 1.2 kgs, 1.3 kgs. The same amount of water weighs 1,000 kgs. Okay, so the density of fluids, density of liquids is 1,000 times that of gases. In a solid, this atom is held in place by the forces of neighboring atoms. So you can model these forces, interatomic forces, by springs. That's what this does. Okay. And the characteristic of a solid is if this atom is here, you can come back 10 years from now and that atom will still be there. For a liquid, that's not true. Every atom moves around and they won't maintain their position, and that's even more true for gases. Okay. So the first half of the chapter is about fluids that are at rest. The second half of the chapter is about fluids that are moving. So for instance, this could be still air and you're flying a plane. In the rest frame of the plane, it's the air that is moving. Okay, so you can look at it that way. So one of the first things we defined was density. Density denoted by rho is mass per unit volume. Okay. And you saw that density for air is, this is in kilograms per meter cube, is 1 kilogram per meter cube. For water, it's 1,000 kilogram per meter cube. And for iron, for solids, it's about 10 times greater than that of liquid. Okay. The next thing we defined was pressure. So fluid will exert a pressure on objects. Okay, and the pressure exerted, so the force that the fluid exerts is always perpendicular to the surface. Okay, and pressure is defined as force per unit area. So what is happening is these liquid molecules are bouncing off the face and they're exerting a force on this face. Okay. You saw that, so atmospheric molecules are bouncing off the surface and they're exerting a force on the surface, and that's atmospheric pressure denoted by P naught. Okay. What is atmospheric pressure? How large is atmospheric pressure? You guys remember? P naught is 15 psi, 15 pounds per square inch. It's in pascals, 10 to the power 5 Newton meter square, and so on. Okay. And in chemistry, you guys talk about 76 centimeters of mercury. and so on. Okay, so this is the unit we'll use most of the time. Okay, so that's atmospheric pressure. Now what this is showing is, this is the pressure as you go deep into a fluid. Okay, so this is the atmospheric pressure on the surface of the liquid. So for instance, this could be a lake. That's the pressure at the surface. And if you go to a depth of h, height h, so this is the additional pressure due to this column of liquid. Okay, so this gives you the pressure inside in a liquid. You saw that as the pressure increases, the force on the wall increases, and that's why dams have to have thicker walls as you go deeper. Okay? Since the force is increasing, you have to counterbalance that with a thicker wall. So this is what is called absolute pressure. That's the actual pressure at the depth. Okay. What most gauges do is they don't measure this. They don't measure the absolute pressure. What they do is they measure this absolute pressure minus atmospheric pressure. Okay. And so this quantity is called gauge pressure. So for instance, well, here's a device. This is a gas in this chamber, and the pressure of the gas is atmospheric pressure plus that. Okay, so here's a device that is measuring absolute pressure. So the pressure of this gas is P naught plus rho GH. Okay. But most gauges measure this quantity. So we talked about this. For instance, what's the pressure in your tires? In your car tires? 30 psi. Okay. And that's a gauge pressure. So the actual pressure, so that is P minus P naught. So the actual pressure is P naught plus 30 psi. And this is 15 psi, so the actual pressure is 45 psi. Okay. We saw that to think about pressure, you can think of it two ways. The pressure a fluid exerts. So for instance, a gas molecules are bouncing off the walls, and that's so when they change their momentum, the wall exerted a force on the molecule, and the reaction force is the gas exerting a force on the walls, and that's how pressure arises. Okay, so for instance, in this wall, there are billions of molecules hitting every centimeter square per second, billions of collisions happening. Okay, you can think of pressure as also the weight of a column of air all the way to space of unit area of cross section, 1 meter square. Okay. So when we say atmospheric pressure is 10 to the power 5 newtons per meter square. So if you take a meter square, this column of air all the way to space weighs that much, 10 to the power 5 newtons. Okay, that's what that means. So for instance, if you were at this height, now the column is smaller, so the pressure will be smaller. Okay, what will be the pressure here? 0. Okay. We use a barometer to measure pressure. Okay. In a barometer, this is perfect vacuum. Okay, so what a barometer is essentially doing is, so here's a column of air. So it's what this is a scale balance. It's balancing this weight against that. The barometer is doing exactly the same. It's balancing this column of mercury with this column of air. They both have the same width. Okay. So the weight of this column of mercury is equal to the weight of this column of air all the way to space. Now, interestingly, the pressure at a depth, okay, the pressure at this depth is the same. Okay, it doesn't matter the pressure, what is the shape of the liquid column. It's the height that matters. Okay. All right. So we saw that we asked the question: why is this slab of air not falling down? This has a weight. This slab of air has a weight. And the reason it's not falling down is because the pressure at the bottom is higher than the pressure at the top. Okay? So that pressure difference is balancing against the force of gravity. Okay? And so this guy is negative. Okay? Anyway, so this led us to the conclusion that the atmospheric density decreases exponentially. So what this formula is saying is, if you go this is about 9 kilometers, about 9 kilometers up, this becomes 1 over E, and the density is about 35% the density, this is ground state density. So the density of air 9 kilometers up is 35% that of ground density. Okay? That is the height of Mount Everest. So on top of Mount Everest, the density of air is 35% that of ground density. Okay. Denver, which is only about mile high, 1.6 kilometers up, the density is already decreased to 80%. Okay. And then the next thing we studied was Pascal's law. So if you have a enclosed fluid and you increase the pressure, so let's say, okay, so here's an enclosed fluid, these are pistons, okay. Right now the pressure here is 1 atmosphere, the pressure here is 1 atmosphere. Now you can increase the pressure at this point by applying a force. So here's what we've done. We've applied a force and we've increased the pressure at this point. Let's say we've increased the pressure at this point by 1/10 of an atmosphere. What Mr. Pascal realized, that increase in pressure at any point is transmitted undiminished to every point in the liquid. What that means is if you increase the pressure at this point by 0.1 atmosphere, at every point the pressure increases by 0.1 atmosphere. Okay, so that increase in pressure is transmitted to this point as well. Okay? And so that ideal leads us to hydraulic presses. So you increase the pressure at this point by this amount, that same pressure is applied at that point. And so F2 is A2 over A1 times F1. This is the input force, and that's the output force you get. Okay, and if this area is 100 times larger than this area, this device becomes a force multiplier. The output force is 100 times greater than the input force. Okay, and 100 times is fairly easy to do. It's you increase the radius by a factor of 10. So the input pipe is like that, and the output pipe is like that. Okay, so that's easy to do. So what does this Pascal's law say? Pascal's law says an increase in pressure at any point on an enclosed fluid is transmitted undiminished to every other point in the fluid. Okay. You increase the pressure here by 20 psi. Everywhere in the liquid, the pressure increases by 20 psi. Okay, and then we saw that, so if a fluid is in a gravitational field, we saw that, I mean, all this is in a gravitational field. You saw that the pressure in the fluid increases with depth. So the pressure here at the bottom is higher than pressure at the top. So any object immersed in a fluid experiences an upward force. And that's the buoyant force. Okay? So here's a rock, there's the force of gravity on the rock, and there's the buoyant force on the rock. Okay? Now, if the weight of the object is greater than the buoyant force, then the object will sink. Okay. If the buoyant force is greater than the weight, then the object will rise up. Okay. And if the buoyant force is equal to the weight, the object will float. I mean, it'll remain at rest underwater. Okay. So, for instance, the human body is our buoyant force is almost equal to our weight. Yeah. So, we wouldn't sink if we didn't panic. Okay. Mr. Archimedes told us how large this buoyant force is. Okay. And what Mr. Archimedes realized, the buoyant force is equal to the weight of the liquid that was displaced. So when you immerse this object, you displace that much liquid. And this force is equal to the weight of that liquid. Okay? And so the buoyant force is the weight of the displaced liquid. This is the density of the liquid, that's the volume displaced times gravity. Okay? So the buoyant force is equal to the weight of the fluid that was displaced by the object. So what this is showing you is a floating object. When an object floats, the buoyant force is equal to the weight of the object. Okay, and you see the buoyant force is equal to that much liquid that was displaced, weight of that much liquid that was displaced. For an object to float, its density, the density of the object has to be less than the density of the fluid it's in. Okay? So that's only when an object will float. Okay? So when an object is floating, for instance, this iceberg is floating, its density is less than the density of water. Okay? So the density of the object is less than so this number is less than 1. Okay? And that is equal to the displaced volume. There's the displaced volume divided by the volume of the object. There's the volume of the object. Okay? And so that number is also less than 1. All right. Again, for an object to float, its density has to be less than the density of the fluid. Okay. All right. So we had learned all of that last time. Now we'll study fluids in motion. Okay, so this is new stuff. So fluid dynamics is what we'll study. All right, let's look at this. What is this? What do you think that is? That's smoke from a cigarette. Okay, and let's see what's happening. Okay, so the cigarette is somewhere down there. What the burning cigarette end does it heats air around it, and the air expands. It gets lighter than the surrounding cold air. So the density of that warm packet of air is less than the density of the surrounding cold air. Okay. So there's warm air. Oops. There's the warm air. Density of warm air is less than the density of the cold air. Okay. and so this packet of air will rise. Okay, so there's a net force on it and it's accelerating, and whenever this is accelerating, it's going faster and faster. Okay, and the reason you can see this is because of the ash particles and stuff like that, smoke particles. That's why you can see that packet of warm air. Okay, so this packet of warm air is rising, it's going faster and faster. Okay, below a critical speed, there's a nice laminar flow. And once the air packet gets faster than a critical speed, the flow becomes turbulent. Okay. This is bad news. Turbulent flow. Okay. All right, so anyway, okay, so when there's laminar flow, there's friction in a liquid. It's called viscosity. When there's laminar flow, the friction is less. When the flow becomes turbulent, the friction increases. Okay, so so let's see. Okay, so here's a blood vessel. There's blood flowing, and here's some plaque deposit, and we'll see this becomes turbulent flow. And so to maintain the same flow rate, the heart would have to work harder. Okay. How long does the heart work? What's that? Yeah, every day, 24/7. So let's say you have plaques. Now for the rest of your life, the heart is having to work harder. Okay. So there's the flow rate, okay, through a pipe. Here's the pressure difference that's you have to maintain to maintain this flow rate. This is flow rate is gallons per minute or whatever. Okay. There's the pressure difference. There's the viscosity, which measures the friction in the fluid. If you decrease the radius of the thing by 10% to maintain the same flow rate, so you can do this calculation, that's 0.9 to the power 4, that becomes 65. The pressure you decrease by R by 10%, the pressure has to increase by 35%.
What's that next to the 8?
I'm sorry?
What's that next to the 8?
This is eta. We'll learn about this. This is the viscosity. Okay. And that's friction in the fluid. Okay. So again, you decrease this by 10%. Okay. All right. Okay, so even before we've started this lesson, what we have seen is the following. Okay, this is laminar flow, and we'll tell you what laminar flow is in a second. So this is laminar flow, meaning if this molecule was traveling like that and this molecule was traveling like this, they will remain neighbors. Okay. Turbulent flow is here's one molecule and here's another molecule, and you don't know what will happen. Just okay, they won't remain neighbors. Okay, this is laminar flow, which is good. This is bad. Okay, when do you have turbulent flow? Above a critical speed. If a liquid moves faster than a certain speed, then you have turbulent flow. And that characteristic speed is characterized by Reynolds number. Okay, we'll come to that. Okay, so the motion of real fluids is very complicated and not fully understood. We'll discuss the flow of an ideal fluid. An ideal fluid is a frictionless fluid. There's no viscosity. All real fluids have friction to them. You guys understand? Okay, so let me ask you. Between honey and water, which one do you think has more friction? Which is more viscous? Honey, obviously. Okay. So, and you know what that means. If you want to pump 10 gallons of honey versus 10 gallons of water, you have to work harder to pump honey. Okay. All right. So, fluids in motion transition from steady laminar flow to turbulent flow above a critical speed. Okay, so after a certain speed is reached, then the flow becomes turbulent. Okay, characterized by a Reynolds number. Here's a quote I like. I don't know if you've heard the name Heisenberg, but he was one of the guys who was instrumental in inventing quantum mechanics, or if you want to say that. Okay, so he's a contemporary of Einstein, of the same league as Einstein. Okay. One said, given the opportunity, so when I meet God, I'm going to ask him two questions. Why relativity and why turbulence? I really believe he'll have an answer for the first. So nobody understands turbulence. Okay, that's the point. All right, but it's bad news. Okay. So, for instance, so here's a plane flying, and if the angle of attack is too large, and this air becomes turbulent, then the drag on the plane increases and the lift decreases. Okay, so you might fall out of the sky. So you don't want that. Okay. And you saw the other example. You saw that you get plaque in your arteries, and now your heart is starting having to work harder, okay, for the rest of your life. Okay. All right. So when turbulence sets in above a critical speed, resistance increases. Okay. So when turbulence sets in, there's more resistance, and to pump the same amount of fluid, the pressure difference you have to maintain is higher. Okay. It takes a lot more energy to pump fluid when turbulence is present. Okay. So for instance, well, why do we have to worry about this? I gave you some example. It happens every day in our lives. The city has to pump water to your house. If there's turbulence in the pipes, there's always turbulence at a certain point, but if they want to minimize it, if there's turbulence, then their pumping cost is high. Okay? And that's an everyday thing. So turbulence is characterized by chaotic changes in pressure and fluid velocity. Again. So turbulent flow can occur in large arteries, at branch points, and in diseased and narrowed stenotic arteries. So here's a stenotic artery. Okay. Turbulence decreases flow rate at any given perfusion pressure. So perfusion pressure is, okay. So if you have friction in a fluid, to pump fluid, you have to maintain a pressure difference. And perfusion pressure is this, P2 minus P1. Okay. And to maintain a certain flow rate, okay, so in this pressure difference is less than this pressure difference for the same flow rate. Okay, so it's costing you more. P2 prime, P1 prime. Okay, so P2 prime delta P prime, delta P prime is greater than delta P. So to maintain the same flow rate with turbulence present, it is costing you more. Okay? or if this is your heart, it's having to work harder. Okay. Okay, so there's turbulent flow, and that's what this graph is showing you. So for a given flow rate with turbulence, again, so you have to maintain a higher pressure to maintain the same flow rate. With laminar flow, all you need is this pressure difference. Okay. So viscosity is the friction in fluids. What does friction do when you move an object? So when I push this cell phone on the table, what did friction do? I'm sorry? It opposes motion, and what did it do? It converted kinetic energy into heat. Okay, so it converts good energy into bad. Okay, so it converts mechanical energy into bad. So you, if you push this fluid, and if there's viscosity, it's converting that motion of the fluid into heat. Okay. Viscosity characterizes the degree of internal friction in the fluid. Okay. So viscous forces causes resistance when two adjacent layers of fluid move relative to each other. So if this layer is moving relative to this layer, viscosity will cause a friction between them. So viscosity causes kinetic energy to be converted into heat. Okay, so we will talk about laws that apply to ideal fluids. Okay. So ideal fluids are non-viscous. Okay, all real fluids are viscous. Flow is steady, meaning, okay, so the velocity at a given location is not changing. So you have a steady flowing river, the velocity is constant. It's not a function of time. Okay. Fluid is incompressible, meaning you don't change the density of the fluid. But we'll apply all these to air as well. So we'll consider situations where the density is not changing much. Okay. But anyway, we are just talking about an ideal fluid. And it is also irrotational. Irrotational just means it doesn't have any eddies in the flow. Okay, so everything we talk about doesn't apply when eddies are present. Okay, and the name comes from the following: if you put a little fan paddle, if there's an eddy, the paddle will rotate. So irrotational means if you put a paddle here, it won't rotate. This is irrotational flow. This is not irrotational flow. Okay, you guys understand? Okay, so the first equation we'll study is the following. Okay, so here's a pipe where you can see that the width of the pipe is changing, the area of cross section is changing. Now, if the fluid is incompressible, let's say 10 gallons a minute flow in here. There's no leak in the pipe. How many gallons are flowing out? 10 gallons a minute. Okay? So if 10 gallons are flowing in and 10 gallons are flowing out, that means this is the flow rate, area of cross section times the velocity of the fluid at that point is equal to area of cross section of the pipe times velocity of the fluid. Okay? So if the area increases, the velocity decreases. Okay? Or if the area of cross section decreases, the velocity increases. Okay? And you guys have seen this. I don't know if you guys have used a hose to water a garden. Okay. And you want the water to go further, what do? You pinch the opening, okay, or close the opening a little. You decrease the area and the velocity goes up. Okay. So we all intuitively know this law. Okay. So that's the equation of continuity. Okay. Now, the next important equation we'll study is Bernoulli's equation. Okay. So here's the deal. So now we're looking at a pipe where the area of cross section is changing and the elevation is also changing. Okay. Now here's two things that happen. Okay. Since the area of cross section increased, the fluid velocity decreased. Okay. Okay, let me answer this. Okay, so since the area of cross section increased, the fluid velocity decreases. Okay. So there's another reason the fluid velocity will decrease. Okay, when you toss a ball up, what happens to the velocity? Decreases. Why? Because kinetic energy is being converted to potential energy. So that's why fluid velocity will decrease as well. Okay? All right, so all that is taken into account by Mr. Bernoulli. Okay? So what he realized was the following, that so for a fluid moving in this situation, what Mr. Bernoulli realized was, if you take the pressure at any location, the kinetic energy per unit volume, and the potential energy per unit volume, the sum of those three quantities is the same at every point. And that's Bernoulli's equation. Okay? So P1, this can be any, P1 can be any point and P2 can be any point. So the sum of those three terms is constant at all points. And that's Bernoulli's equation. Okay? So this is something that you want to remember. Okay, so one of the most important applications of this is the following. Okay. And let's make sure you understand this. Okay, let's say y1 and y2 are the same. Okay, so this is equal, and if, so I'm going to write this, P1 plus 1/2 rho V1 square equal to P2 plus 1/2 rho V2 square. Okay, so this is y under the condition that. Now, if the fluid is flowing faster, if this one is greater, then this has to decrease. Okay? So because the sum of these two terms have to be constant, if at a location V1 is higher, then this has to decrease. Did you guys understand that? All right, so let's see how that works. Okay, so airplane wings are designed like this. This is an airfoil. You shape them like that. Why do you shape them like that? Okay, so this curve, okay, let me draw a more exaggerated curve. Okay, so air is flowing like this, and it has to go around like that. This air has to cover a larger distance, so it has to move faster than this air. Now, when this air is moving faster, what happened to the pressure? When the air is moving faster, the pressure decreased. Okay, so pressure at the top is less than pressure at the bottom. And you generate lift. The force of lift is pressure at the bottom minus pressure at the top times the area of the wing. Okay, so that's how you generate lift. That's how a plane stays up in the air. Okay. Did you guys understand that? All right, so hey, Gabriel, how you doing?
Doing all right. Thank you for asking.
All right. It stayed dry. I guess it's not raining yet.
Yeah, it's on and off coming in.
Okay.
It's worse on the freeway.
All right, so Bernoulli came up. So Bernoulli was one who discovered the relationship between fluid speed, pressure, and elevation. Okay? And like we said, pressure plus kinetic energy per unit volume plus potential energy per unit volume. The sum of those three is constant.
Is that like rho, like density? I always
Yeah.
forget what that is density.
Rho is density of the fluid. Okay? Okay, so for this fluid, the sum of those three terms will be the same at every location. Okay? And again, this applies to an ideal fluid, frictionless, incompressible, and all that stuff. But we abuse it, and we'll apply it to real fluids and all that. So when we apply it to real fluids, it's an approximation, but we're happy with it. All right, so here are some effects that you might experience. Okay, again, what is it that I want you to remember? If the velocity increases, what happens to the pressure? Pressure decreases. Okay? So I want you to remember that for the rest of your life. Yeah. All right, so let's apply this. Okay, so let's say you're driving next to a semi. This air, now the gap is pinched, so this air here has to flow faster. This air is flowing faster than this air. So you feel a net pressure in that direction. So you feel an attractive force to the semi. Have you guys experienced this?
Mm-hmm.
Okay. All right. So. Okay, so you saw how an airfoil generates lift. Because of the shape of the airfoil, this air is moving faster than this air. So the pressure at the top is less than the pressure at the bottom. And that pressure difference, okay, so the force of lift is the pressure at the bottom minus the pressure at the top times the area of the wing. Now, you guys have been on planes and stuff like that. Okay, so when the plane comes into land, it's going slower. Okay, so this pressure difference decreases. Okay, so for instance, if the plane were at rest, the pressure difference would be 0. So when it's coming into land, this pressure difference is decreased. Why isn't the plane falling off the air? There you go. You have to increase, when this decreases, you have to increase the area of the wing. You're not slapping on new wings. We extend flaps. You increase the area. Okay? All right, so here's a computer simulation showing you that this air is moving faster than the air at the bottom. Okay. You don't want to increase the angle of attack too much because you don't want turbulent flow. If you get turbulent flow, then drag increases and lift also decreases because the pressure is unpredictable then. So here's the Magnus effect, and we have a tennis player here, so she probably knows what's going on. But anyway, so here's this tennis ball going in that direction. So the air is flowing like that. Okay? And this tennis ball is hit with a top spin. Why do you hit it with a top spin? Okay, so here's why we hit it with a top spin. Okay, so you've hit the tennis ball there. There's the baseline, boundary line on the other end. Okay, and you want the ball to fall within the baseline, not outside of it, of course. Okay, so when you hit it with a spin, now what's happening is because of the felt and all, the air here has to flow like that. Here's the airflow pattern. Now this air is flowing a much greater distance than this air. The pressure here is lower. okay? And so there's a net force like that. And that'll make the ball fall inside the baseline. And what this does is, you know, it's very hard to control the force, but with the top spin, the harder you hit, the more spin there is, the greater the force, and the more likely it is to fall inside. So you guys see that? It gives you much more room for error. Okay, if you hit without spin, you hit it too hard, it'll go outside the baseline, and that's a very hard thing to control. So the greater the top spin, and the harder you hit, the more likely it's to fall inside. Yeah. You guys have all used bottle sprays, okay? And here's, so all those sprays, what they do is they blow air like that. So air is blowing like this. Soon as air blows, what happens? The pressure there decreases, okay? And the pressure there decreases, it becomes less than 1 atmosphere, and 1 atmosphere of air pushes this fluid up, the fluid gets caught and it's sprayed up there. Okay. How much pressure do you have to decrease there by? Equal to the height of this liquid. Okay, so for it to work, the amount of pressure you have to decrease is the liquid has to rise up that much. Okay. So pressure at this location, P naught minus PL has to equal density of liquid times G times H, okay, for it to get caught. So you have to blow the air fast enough. Okay, again, what is viscosity? That's friction in a fluid. And here's how you measure that. Okay, so let's say you put a flat board there, and here's a flat board. Here's the liquid, and okay, so there's the thickness of the fluid. Okay. And what you do is you measure how much force do you have to apply on this top board to get it to keep it moving at constant velocity. If there was no friction in the liquid, you don't need any force to keep it moving. Okay, so for instance, which one has greater viscosity, air or water? Water, obviously. So here's a demonstration. You played air hockey, you get the puck moving, and it'll keep moving for a long time. The friction force is very small. You take a water tank, put a piece of wood, and get the piece of wood moving in the water tank, it'll stop much faster. Okay? Did you guys understand that? Okay, so here's how we'll measure viscosity. What force do you have to apply to keep this slab moving at constant velocity? Okay, if there was no friction, why are you having to apply a force? Because of the friction force in the opposite direction. Okay. All right, so this is the force you have to apply, and this is eta, which is measuring the viscosity of the fluid. Okay, so the greater force you have to apply, the greater the viscosity. Okay. So this number, so for instance, for honey, if this liquid was honey, you would have to apply a greater force as opposed to water.
Is that a dimensionless?
No, it's got dimensions, so you want to calculate the dimensions. F, L, V, area. Newton, meter, meters per second, meter square. So Newton, seconds. All right, so well, I want to keep this. So eta is the viscosity. Okay, so what this equation is telling you is the following. Okay, so if there was no viscosity, if this was zero, to maintain a flow rate, you didn't have to have a pressure difference. Okay? So once you get the fluid moving, if it was frictionless, then it would keep flowing forever. Okay, you could pump oil from Prudhoe Bay to the south of Alaska without having to spend any money on electricity. But unfortunately, there's viscosity. Okay, so you have to maintain a pressure difference. Okay, so the flow rate is the pressure difference times pi to the power of R4, R to the power 4, divided by 8 eta L. Okay, L is the length of the pipe. Okay, so this pressure difference, that's your electricity cost. Okay, so when you pump oil down from Alaska, from Prudhoe Bay down to Alaska, okay, so there's the pressure difference that you have to maintain. Do you guys know that the pipe, they have heater elements around the pipe? They heat the oil. Why do they do that? What? That's right. So you heat it and you decrease the viscosity. So to maintain this flow rate, now you have to maintain less pressure difference. Your costs went down. So your costs went down, obviously, more than the heating costs. Okay? So the point of that story is you'd better learn your physics well. Pay attention in your physics classes. All right? Did you guys understand that? Okay. All right, that finishes this chapter.